No, fido cake. No, fido. No, fido. So good evening, everyone. Am I audible? Hello? 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 So today we are starting with pulmonary graphics. So what is the importance of pulmonary graphics? Understanding the physiology of the lung, the normal lung, and understanding the pathophysiology of the disease lung, and how this respiratory support systems like the ventilators will help in this should be better understood so that we can achieve the ultimate goal of the neonatal ventilation, that is the optimizing the gas exchange with minimal ventilator injury. So we know all the advanced ventilators are having the microprocessor based flow sensors, which will help in displaying the pulmonary graphics at the bedside in the ventilator screen. But unfortunately, most of the clinicians are not using this pulmonary graphics in their day-to-day ventilator settings. So today we will discuss with the use of the pulmonary graphics and along with the limitations of the pulmonary graphics, so that along with the bedside capillary blood gas, X-rays, this also can be used as a tool which will help in adjusting and optimizing our ventilator settings. So these are the usual ventilator graphs which we are using in our unit. So the importance of pulmonary graphics is one, the clinician, it will help the clinician to assess the patient's respiratory physiology and pathophysiology, and also helps to optimize the ventilator settings. It will reduce the ventilator-induced lung injuries. It will help in evaluating the infant's spontaneous respiratory efforts and help in facilitating the weaning process. It will also help to assess the therapeutic response to the pharmacological agents. It will also help in detecting the tube leakage and secretions and prevent the disastrous consequences. And this, it helps in improving the quality of the care. So we know how is the flow measured. The flow is measured by using mainly the pneumotachometer and the hot wear anemometry. And different ventilators have different methods. Most of them are now hot wear anemometer. So before going to hot wear anemometer, just a few words about the flow sensor, which is pneumotachometer. We know pneumotachometers are normally placed between the Y piece of the ventilator and the endotracheal tube. And inside the sensor, there is a tubular or a lamellar structures, which will ensure the laminar flow. And it will create a small resistance to measure the pressure difference along this resistor. So this pressure difference is then measured using a differential pressure transducer, which is connected to a small proximal and a distal pressure line. And we know the pressure will be higher on the proximal side, that is close to the Y piece during inspiration, whereas it will be higher on the distal side close to the endotracheal tube during expiration. So this pressure difference is proportional to the flow. And the problem and important advantage with this is it is even extremely sensitive, even with the small flows, but it can be affected with humidity and secretions. Now, most of the ventilators are with hot wear anemometer flow sensor. What is the importance of hot wear anemometer? In hot wear anemometer, actually, there is a two wires, which are platinum wires, which are heated to a high temperature. And when the air flows through it, when the gas flows through it, that will be cooled. So that current used to reheat it is measured, and from that we can identify the flow in the tube. So the hot wear anemometers use a hot wear placed within the sensor with airflow changing the temperatures of the wire, which influences the electric current through the wire. This change in the electric current is sensed by a microcontroller, and it is proportional to the flow in the tube, thereby allowing the microcontroller to estimate the flow in the tube. It is less sensitive to small flows, but it is less prone to gas humidity and water rainout when compared to the pneumotachometer. So now, before going to the proper topic, just a few words about the limitations of the pulmonary graphics. We know there is no standardization of the techniques of measurement of pulmonary graphics or mechanics or of the display formats across the ventilators from different manufacturers. So it will be different in each ventilator. So we have to know the ventilator which we are using in our unit, and we have to we should know more about that one. So unfortunately, this can be distorted by improper scaling of the axis, and sometimes the direction of the flow volume loop in one ventilator will be in clockwise, another ventilator will be counterclockwise. In some ventilators, the inspiration in the flow volume loop is below the x-axis. Sometimes it will be above the x-axis. So we have to know what type it is in our own ventilator. So clinicians should learn to interpret the screens of ventilators used in their institution and how exactly the measurements are obtained and analyzed. Another important thing is that actually this doesn't measure the regional variations in lung function, particularly in cases with a non-homogeneous lung diseases. So, and again, one important thing is that it's only measuring the mechanical properties of the lungs and airways, but it is not measuring the true gas exchange. So the information obtained from the pulmonary graphics and the monitoring should be supplemented by the information obtained from history, clinical examination, laboratory tests, including blood gases and chest imaging. So now going to the ventilator graphics. So mainly we have two things. One is scalars and one is loops. So the measured parameters are flow, pressure, and time. And the calculated parameters are volume, compliance, resistance, and work of breathing. We know volume is measured from flow and time. This is the integral of the flow. Compliance, we know change in the volume by change in pressure. Resistance is the pressure used to drive the flow divided by the volume. And work of breathing is the force into displacement, and which we can calculate from the area under the pressure volume curve. So all these things are calculated parameters, which are seen on this right side. So the normal values of compliance. Compliance is a measure of change in the volume resulting from a given change in pressure. The normal values are 1.5 to 2 ml per centimeter H2O per kg. This is in the normal healthy newborn. Then airway resistance is defined as the pressure gradient which is required to move the gas through the airways at a constant flow rate. This R is equal to P1 minus P2, the pressure gradient divided by the volume. The normal value is 20 to 40 centimeter per H2O per liter per second. Then work of breathing is force into volume displacement. So this is a force into volume. So actually that is the area under the pressure volume curve. Now coming to scalars. What is scalars? We have three scalars, that is pressure versus time, flow versus time, and volume versus time. This is a relationship between the respiratory parameters and time on a breath-to-breath basis. These are the three different scalars. One is pressure scalar, one is flow scalar, and the lower down is the volume scalar. This is how it is represented in the ventilator. And the loops are the in loops, these parameters are presented relative to each other. That is pressure to volume, flow to volume on a breath-to-breath basis. And what are the basic phase variables? What is trigger? Trigger is what? Which causes the breath to begin. May be either a time triggered or it might be a patient triggered. Patient triggered means it might be a flow, volume or flow, pressure or the diaphragmatic activity in a case of a NAVA. And limit means what regulates the gas flow. It can be either pressure or can be volume. Cycle means what causes the breath to end. Can be either time cycle or it can be a flow cycle. So now coming to the proper topic. First we are dealing with the pressure waveform. So what is pressure waveform? So this is the pressure waveform. This is the pressure waveform in a pressure control mode. So here we can see that the pressure waveform represents the airway pressure throughout the respiratory cycle. We know all the newborns at the beginning of the ventilation will require some degree of PEEP. So that the beginning of inspiration or the end of inspiration, we can see that actually the waveform will start from the baseline pressure, that is the PEEP. Then the pressure increases and reaches the maximum pressure, that is the PIP. Then after that, it will be remaining constant till the end of the inspiration, that is the end of the TI. Then the exhalation valve will open, then expiration will start. So the pressure will again drop and it will reaches the baseline, that is the PEEP. So this is how you will interpret the pressure control mode, sorry, the pressure scalar. And the area under this pressure waveform is the mean airway pressure. The difference between the PIP and the PEEP is the delta P. And this is the pressure scalar in a volume control mode. So here in the pressure control mode, we can see that after reaching the maximum pressure, the pressure is maintained at a constant level. And in the volume control mode, actually flow will be constant. So actually from the pressure waveform itself, we can understand what is the type of ventilation is going on. Is it a pressure control or a volume control? Okay. Then, so that is the first important point. Then we can know about the map. Then third important thing, from the pressure waveform, we can identify the trigger, whether it is a patient triggered ventilation, patient triggered breath or a mandatory breath. And also we can assess about the adequacy of the flow. So again, this is a type of ventilation. So I already told in the pressure control mode, we can see that after reaching the maximum pressure, it is maintained constant. So from seeing the square waveform in the pressure scalar, we can identify that is a pressure control ventilation. The volume control, we can see the flow waveform is having a square waveform. So after reaching peak flow, it is maintained at a constant level. That is what we see in volume control. So from quickly itself, we can assess what is the mode of ventilation going on. Coming to map. Map is very important because it determines the oxygenation. So from the pressure waveform, we can see the map and we can also see how it affects or the different factors affecting the map. So to increase map, we can either increase the flow. So we can see by increasing the flow, this slope will be more steeper. So the area under the curve will be increased. Then second, we can increase the PIP. So the peak inspiratory pressure is increased. So again, the area is increased. We can increase the PEEP. So then also this area is increased. Then we can lengthen the inspiratory time. So more area will come under this curve. And we can increase the rate. So this breath will come here. So that also will increase the area under the curve. So map is increased. So for map increasing, these 5 things has to be done. Now coming to the adequacy of the flow. So when we can say the flow is adequate from seeing a pressure waveform. So the flow marked on the ventilator will be adequate when it allows the desired pressure to be reached at the end of the 1/3 of the inspiration. So the pressure which we wanted, its maximum pressure, will be reached within 1/3 of the inspiratory time. Should not be reached very fast or it should not be reached very slow. So within a 1/3 of the inspiratory time, this maximum pressure will be reached. So the slope of this ramp should last within the 1/3 of the inspiratory time. So seeing the pressure waveform itself, we can identify whether the flow is adequate or not. So this flow, this pressure waveform, we can see that the phase 1, that is, this is so prolonged and the pressure, the desired pressure is not reached even before the end of inspiration, just reached before the end of inspiration only. So the flow is very low. So we have to increase the flow. This we can see that the flow is very high. Even before starting of the inspiration itself, the maximum pressure has been attained. So this means that flow is too high. That can cause lung injury. So from the knowing the pressure waveform itself, we can identify the adequacy of the flow also. Now, this is another important thing, that is a pressure overshoot, the same as what we have just mentioned. So if the flow rate is too high, this is the pressure waveform, this is the flow waveform. In the pressure waveform, we can see that the flow rate is too high, the delivered pressure will be attained very rapidly. So that will create a condition known as pressure overshoot or ringing. So we can see a notch or a double peak at the PIP. And again, in the flow waveform, we can see an inspiratory bump. So these two things help us to identify the pressure is overshooting because of the very high set flow rate. So the all modern ventilators have this rise time, which will help in adjusting the flow rate. So it will not be rising too far. If it is rising too high, we can adjust the rise time so that it is a semi-quantitative means of reducing the inspiratory flow rate. This pressure should not be overshooted like this. So it will cause ventilator injury. Now, another important thing which you can learn from the pressure waveform is whether it is an assisted or a controlled breath. So in assisted breath, we can see that negative deflection, which is actually the trigger from the baby side. The completely controlled breath, there will be no negative deflection. This is how we will identify an assisted breath or a controlled breath. So what we this one is actually pressure control. And this one is volume control. That is why the wave form is looking like a triangle method. Now coming to the flow waveform. Actually, in the scalars, the most important one is the flow waveform because we can gather a lot of information from the flow waveform. And it is a little bit more complex because it has got a positive deflection and a negative deflection. So we can see that there is a baseline here. This baseline means that is a zero flow state. That is no gases entering or leaving the airflow, leaving the lungs. So here we can see a positive deflection means that is gases flowing into the patient. Here we can see a negative deflection, gases flowing away from the patient. And this is inspiration and this is expiration. So at the beginning of the inspiration, what will happen? There will be an acceleration of the flow till it reaches the maximum inspiratory flow rate. That is peak inspiratory flow rate. The middle of the inspiration, we can see. And it slowly decelerates, and finally touches the baseline. So that it reaches the zero flow state. So from this zero flow state to this zero flow state is the TI, the inspiratory time. Now again, coming into the expiration, we can see the flow is reversing. So flow again, it accelerates. That is the expiratory flow will accelerates, reaches the peak expiratory flow rate. Then it again decelerates and reaches the baseline, reaching the zero flow state. So from here to here, it is the TE, that is the expiratory time. So there is a peak accelerating inspiratory flow, decelerating inspiratory flow. Similarly, there is accelerating expiratory flow and a decelerating expiratory flow. So ideally, this flow should, the inspiratory flow should touch here. Similarly, that is the zero flow state. And this expiration also should touch the zero flow state. That means the lungs is completely emptied to the FRC. So this is very important. All this air leak, all this air trapping will be identified after properly understanding this flow waveform. So what we see is this, the previous waveform was actually pressure control ventilation. That is why we saw that spike pattern. In a flow scalar of a volume control, how it will appear? We already discussed that in volume control ventilation, the flow scalar will be having a square waveform. Why? Because we know once the inspiratory flow reaches the peak level, it will be held constant during the entire period of inspiration, and it will be, this exhalation valve will be open only at the end of the inspiration, and then the flow will be going out. So it will create a square waveform. So this is how we can identify the volume control or pressure control from the flow waveform. So this is same. So these are different flow patterns, what I already told. In volume control, it will be square, and in pressure, it will be decelerating. And the sine waveform is usually seen in the spontaneous breathing. So the most important thing what we see is here is first we can identify what is the mode. Second important thing which we can learn from the flow waveform is how to optimize the TA. Then another important thing is air trapping, airway obstruction, and leaking. So can you identify what is happening here? We already discussed the flow waveform, what is a normal waveform, and what is happening here. If you can see the waveform closely, we can see that the flow has already reached the zero flow state, but still the inspiration is continuing. So this is what is known as inspiratory hold. That is actually it is a zero flow state. Already the pressures has been achieved. The pressure already been achieved. The flow has become zero, but baby is in a state of inspiratory hold. The lungs is full filled with air. Baby wanted to exhale, but since the ventilator already set as I time as a fixed duration, the baby cannot exhale also, though it will create a asynchrony. So this is actually more harm to the baby because it can cause a short TE. The expiratory time will be shortened, and that can lead to air trapping. So what we should do here? So what we should do here? In such a condition, but ideally, so from the flow waveform, we can identify the TI, is it optimum or not? So depending upon that, we can change. So what we should do here? Yeah, we should decrease the TI. Otherwise, next option. So what is the next option? We can also use a flow cycling. So in patient-triggered ventilation, which are particularly time cycled, the clinician will set a inspiratory time, and the exhalation valve would close and the pressure and flow will be delivered until this exhalation valve is open at the end of inspiratory time. So during time cycling, what will happen is that, so actually this inspiratory hold is a problem. So we can change into a other thing, that is flow cycling. So what is meant by flow cycling? So the flow cycling is taking care of the mostly a natural breathing pattern. That is actually the baby's spontaneous inspiratory flow is taken care. So the ventilator will note the maximum peak inspiratory flow rate of the baby, and when the inspiratory flow rate decelerates, but before it is reaching the zero flow state, the exhalation valve will be open. So at what point this exhalation valve will be open is determined by the clinician chosen termination sensitivity point. That is, if we can choose between 5 to 25% or whatever it is. So a particular point we have already chosen. At that point of time, the inhalation will be cycled off to exhalation. So what is the advantage of this? So actually we are focusing on the baby's inspiratory flow, and ventilator is taking advantage of that. So so actually there are mainly two advantages with this flow cycling. One, it is more natural, it is following a more natural breathing pattern, and it avoids this unnecessary inspiratory hold, but we already discussed. And another important thing is that we know it enables 100% synchrony between the baby and the ventilator, because here the baby initiating respiration, baby is terminating the respiration. Both is done by the baby. And second, it prevents the gas trapping, which I already discussed. What is the problem with the inspiratory hole? That there can be a short, if you are in a time cycle ventilation, the baby is breathing at a faster rate. What will happen? The TE will be reduced. The expiratory time will be shortened. So lungs will not get enough time to empty. So that will cause for gas trapping. So that problem will not happen in flow cycling because ventilator knows when the peak flow is getting reduced, ventilator knows that the baby is going for expiration and ventilator will automatically switch on to the expiration mode. So two advantages. One is 100% synchrony, and again, they will prevent air trapping also. So prevention of air trapping as longer TE can be provided, especially if the infant is using high respiratory rate. Then second important thing, it will adequate, also when the baby is breathing very slowly, it will allow adequate inspiratory time also. So it is not a time cycle, it's completely depending upon the baby's flow. So it will improve the patient ventilator synchrony. So this is the how we are choosing a certain point. That is, here the flow, it is coming down from 25 to 5%. We can either choose it 25% or 15% or 5%. So depending upon the chosen point, the ventilator will changes from the inspiration to expiration and the flow is reduced to a certain amount of that point. So if it is, we are choosing a 25% flow cycling, the ventilator will switch over to exhalation when the 25% of peak inspiratory flow rate has been reached. So, but problem with flow cycling is that it shortens the TI. We already told that can result in a lower MAP. But if there is a higher breathing rate is okay. But if higher breathing is not there, the MAP will be definitely coming down. Another important thing is that during flow cycling, always there will be time cycling also in the background. So the inflation will be terminated by whichever criteria is met first. But in case of large leaks, flow cycling may not work as inspiratory leak flow may not decrease below the threshold chosen for the cycling off. So here we can see the inspiratory hole. We told already we can reduce the I time. And next option is we can change it to flow cycling. So in flow cycling mode, we can see that that inspiratory hole has been gone. And it is a better synchrony also can be achieved. So this is the flow cycling in PSV. Now, can you identify what is the problem with this graph, flow scalar? So here we already discussed that normal flow waveform, how it should appear. The inspiration should reaches the maximum peak inspiratory flow rate, then it should decelerate and should touch the baseline. Here we can see that actually it is not touching the baseline. Actually, it is ventilator has been drawn an artificial line here. It is not touching the baseline. So actually the volume delivered will be low. So what is the problem here is actually a short TI. So we have to increase the TI here. So from the flow waveform, we can identify the TI and we can optimize the TI depending upon the situation. So next important thing, what we are going to learn from the flow waveform is, can anyone identify this situation? Yeah. So here we can see that the expiratory waveform is not reaching the zero flow state. It's not reaching the baseline. Before that, another breath has already been started. So another inspiration has already been started. So this is what is known as air trapping. So previously, the air trapping usually will be in the previous before the graphics. The clinician will be always will be aware of the gas trapping only once the leak had occurred. Once there is an alveolar rupture and air leak, then only it will be identified. But when we have a real-time breath-to-breath analysis of this with pulmonary graphics, it is easy to identify the gas trapping even before the devastating consequences are happening. So the gas trapping occurs when the expiratory flow is less than the inspiratory flow. That means that more gas is entering, but it is not leaving the lung. So actually the expiration is not reaching the zero flow state. So what we should do here? We should decrease the ventilator rate. We should shorten the I time. We should give enough E time for the ventilator, for the lungs to empty. So either we can do it by shortening the ventilator rate also. So the E time will be increased by shortening the I time. Or we can also decrease the flow rate. So this is air trapping. So what is the problem with this graph? So in this graph, we can see that we already discussed that there is a peak expiratory flow rate. But here we can see that the expiratory flow is actually shallow with a decreased peak expiratory flow rate, and it is taking a long time to reach the baseline. So this is what is increased expiratory resistance. This is what we are seeing in a bronchopulmonary dysplasia, having some kind of bronchospasm. So what we should do? So we given a bronchodilator. What is happening? So we can see that after giving a bronchodilator, actually the PEFR, which was short here, has improved. And this long TI actually reduced to short. So the expiratory curve can return to the baseline faster. And the peak expiratory flow rate has also increased. So the resistance has been reduced. So this is air leak. So what is the problem with air leak? We know we are using only uncuffed endotracheal tube, so there will be some degree of leak. But we know most of this leak occurs during inspiration when the pressure is high. Another thing is that leaks are more easiest to recognize on the VT waveform, that is a volume waveform, and the pressure volume or the flow volume loop. But we can also see in the flow waveform, if we carefully goes through it. And one thing is that the significant leak. This is how the latest edition of Goldsmith has depicted the the leak in the flow waveform. So this is the flow waveform. Here we can see that the inspiratory flow is not reaching zero before the next inflation. So here we can see that inspiratory flow is touching the baseline. Here it is not touching the baseline, and ventilator has drawn an artificial line connecting these two. So this is a small leak. This is how it has been depicted in the new Goldsmith. And when there is a large leak, what will happen? When there is a large leak, we can see this airflow is positive both during inspiration and expiration in the flow waveform. We already told that inspiration, the flow waveform will be positive, and expiration, it will be negative. But we can see that this flow waveform is completely positive both during inspiration and expiration. So actually this the leak will divert the gas flow such that the decelerating inspiration, actually there is a decelerating inspiratory flow. It is never touching this termination point. So the gas flow will be diverted in such a way that the decelerating inspiratory flow is never touching the baseline. So this is actually a large leak. So the airflow will be positive both during the inspiration and both during the expiration. And when we see the VT, that is a tidal volume curve, volume scalar, we cannot monitor the VT because VT is actually scaled exclusively into the leak. So it is not possible to see the expiratory part of the volume loop. So what is the problem with this leaking? I mean, finally, if there is a large leak, what will happen? So another important thing that can be associated with this leaking is there will be an auto triggering. We know the ventilator, when it is a patient triggered ventilation, so the flow triggered ventilation, the ventilator will interpret this aberrant flow as a patient effort. This will happen when such a large leak will be misinterpreted as the patient effort, and because it is exceeding the trigger threshold. So what will happen? It will be automatically triggering the breath. So we can see very rapid rates and a very uniform also. So there will be, baby will be having hypocapnia and their lung injury can happen. So what is how we will identify whether it is due to auto triggering or due to the rapid breathing from the baby side? So in auto triggering, actually these flow waveforms will be very uniform in their shape. But in case of just a rapid breathing, there will be some amount of variability will be there. Here we can see all are very similar and very uniform in their appearance. So this is usually auto triggering or auto cycling. So this is because of this significant leak is actually misinterpreting the ventilator as a effort from the patient side because of the amount that is actually exceeding the trigger sensitivity. So the major scalar is over. From flow waveform, actually not much information we can identify. This is how the flow waveform will be there. So here the starting of the inspiration, the inspiratory volume reaches, and at the end of inspiration, the maximum volume is attained. And finally, during expiration, this volume is reducing, and finally reaching the baseline. So this is how the volume scalar appears. So actually air leak can be better identified in a flow waveform. We can see that, sorry, in the volume waveform, we can see that this exhalation part is not reaching the baseline. Means the air has already been leaked out. There is no air, the initial air in the inspiratory part, when reaches the expiration, before the expiration reaching the zero, this air has already been leaked out from the lungs. So it is not touching the zero line. So this is actually shoulder cliff, shoulder fall or shoulder cliff sign madri, but we are seeing in the ventilator. So this is how it is seen in the ventilator graphics. You can see that this volume waveform is not touching the baseline. It's actually cliff madri. Again, it is not touching the baseline. Again, it is not touching the baseline. You can see that cliff sign. This is the cliff sign. So another important use of volume waveform is that we can actually assess the breath, whether it is the tidal volume of this spontaneous breath is adequate or not, whether baby is ready for extubation or not. That is another important use for the volume waveform. You can see this is the mechanical breath, this is the spontaneous breath. Actually, it is low. And we can also assess the ventilator synchrony. If there is asynchrony, the tidal volume will be inconsistent, as like in IMU or SIMU mode. Here we can see the all tidal volumes are almost same, consistent. Here. So that is usually the patient triggered ventilation. This assist control. Now coming to loops. Now, so what is loop? You know, in loop, actually the relationship between the two variables are plotted against each other. And one will be in x-axis and the other will be in y-axis. So, but the problem with the loop is that actually there is no agreed convention. So each ventilator will be having a different way of representing. The other ventilator will be having another way of representing. In some ventilators, the PV loop will be displayed as inspiration in the upside and expiration in the downside. So in the other ventilator will be different. So we have to see in our ventilator how it is represented. Whether inspiration is up, expiration is downward, or it is in the opposite manner, or is it clockwise or in counterclockwise. But there is no agreed convention regarding how it is represented. Now coming to the pressure volume loop. What is pressure volume loop? You know, pressure volume loop displays the relationship of pressure and volume during a single breath. Here we can see pressure is displayed on the x-axis and volume is on the y-axis. So we can see that the origin of the loop doesn't start with zero, because we already know that there will be a baseline pressure which is PEEP. And after that, as inspiration increases, as inspiration begins, there will be a rise in pressure and subsequently volume. And here we can see we are crossing this lower inflection point. And after that, it is reaching the maximum pressures. Then we can see increase in the volume in a steady state. And finally, this is the end of the inflation limb. Then this is the deflation limb, that is during the exhalation. So here also we can see that the expiration starts at C, but here there is a rapid drop in pressure. And that is because this is the upper inflection point. When it is crossing the upper inflection point, suddenly there will be a drop in pressure and it reaches the PEEP. That is the baseline pressure. This is how is the pressure volume loop. And what is this slope? The slope is this AC. This is the slope of this loop, and that represents the compliance. So when the compliance is slow, this PV loop will shift downward and to the right. When there is a good compliance, this graph will shift towards the upward and to the left. So what and all things we can learn from this PV loop? So one is compliance. So compliance is the measure of change in volume resulting from a given change in pressure. We already discussed the normal compliance is 1.5 to 2. So, and another important thing which we can learn from the PV loop is the resistance. So what is resistance? So resistance is that if we are drawing a line from the midpoint of this inflation limb to the compliance axis, that is the inspiratory resistance. Similarly, if you are drawing a line from the midpoint of the deflation limb to the compliance axis, that is the expiratory resistance. So if the inspiratory resistance is high, the graph will be like bulging like this. And similarly, when the expiratory resistance is high, the graph will be bulging towards this axis, towards the y-axis. So another important thing which we can learn from the pressure volume curve is the role of FRC on the compliance. So we can see that in this portion, that is at the area of normal FRC, there is a linear change in volume with pressure. That is the compliance is high. So a slight change in pressure will produce a good enough change in volume. But in this lower end, there is low FRC, that is an atelectatic lung, or in a high FRC state, which is overexpanded like a meconium aspirated lung, we can see that the compliance is actually poor. Even the large change in pressure also, not much change in volume. Here also same. Already lungs has reached its maximum distensibility. So even if we are increasing the volume, we are increasing the pressure again, there is no much change in volume. So these two states, the compliance is low, and we should ventilate the lung at this point. It's a normal FRC. That is the importance of compliance axis. So we have to use the optimal FRC. Now, another important thing which we can learn from the pressure volume loop is the work of breathing. So we know that this A, B, C, E, A, this is a total work of breathing during a single breath. So when the compliance is dropping, that is compliance is becoming low, this loop will be shifting downwards, that is towards the left side. So we can understand that actually the work of breathing is more. Why? Because more pressure is needed to produce the same amount of volume. So when compliance becomes low, work of breathing increases. So we can identify all these things from our pressure volume loop. And another important concept is the upper and lower inflection point. So the upper and lower inflection point, we know here, when the airway pressure is increased, at this point, the lung recruitment will occur when it is passing the lower inflection point. But when we are going here, we can see when we're crossing the upper inflection point here, this is a lower inflection point. We're crossing the upper inflection point. Actually, we are giving more pressure. Actually, lungs are becoming more distended. There is no much change in volume. So our ventilation should be at here and before here. So if you are ventilating below the lower inflection point, actually it will be opening and closing. The alveoli will be closing and opening, and that will cause atelectasis. And if you are ventilating above this upper inflection point, that will cause overstretching of the alveoli, resulting in barotrauma or volutrauma. So these are the important concepts regarding the pressure volume loop. Now we can come to the topic. So here we can see the compliance. Here the compliance, this is a normal compliance, this is green. And this pink one is actually low compliance, and this yellow one, actually the compliance is more. So this might be an RDS or a pneumonia, surfactant deficient state. So can you identify what is this? Yeah, this is actually, we can see the pressure volume loop is actually lying on the x-axis. So that means, and the X-ray also shows typical RDS pattern. So this is a pre-surfactant. So after giving surfactant, what happens? We can see that compliance has improved, and this axis is coming towards to the right side, towards the left side. So actually it is, previously it was falling on the x-axis. Now actually it is going up to the left. X-ray also improved. This is post-surfactant. So can see that the pressure volume curve of both, actually if it is a pressure control ventilation, we can see actually pressure is same, but the volume actually been doubled once the compliance has improved. So before surfactant and after surfactant, the volume has been doubled. From here it was 5, here it is actually more than 10. So the volume has already been doubled when the compliance has improved. So what is auto-weaning in a volume targeted ventilation? We know in volume targeted ventilation, as the compliance improves, the pressure will be automatically decreased by the ventilator to maintain the constant volume delivery. So we can see that. So this is the first, this is the initial thing. Compliance was poor. And when compliance was improved to this one, actually the ventilator has reduced the pressure from here to here and maintained the constant volume. But when we see this graph, we can see that in a pressure targeted ventilation, what will happen when we improve the compliance? Actually, it will lead to, so this was the initial stage, low compliance, it improved to better compliance. So we can see here a large volume is delivered. So what it will cause injury. So what we have to do, that we have, the clinician should be vigilant about this and should decrease the inspiratory pressure accordingly. Because when the compliance improves, the same pressure will deliver more volume. So we have to reduce the pressure. So can you tell what is this already been shown? So this is what is a penguin beak or a duckbill appearance. We can see actually the lung has been distended and reached a beaking point, beaking madri here. So this is actually because of over distension. So what we should, so actually if you are, what we told like in pressure targeted ventilation, if you are not coming down the pressure, once the compliance is improved, the lung will be stretching like this, and it can go into for a pneumothorax. So this is actually a peaking over distension. So we have to decrease the peak inspiratory pressure. So to quantify the over distension, there is a criteria thing. There is a ratio known as compliance ratio, that is E20/C. That is a numerical representation of the degree of the lung over distension. It measures the last 20% of the dynamic compliance to the total compliance. And if the ratio is 1 or more, it is normal. If the ratio is less than 0.8, that means that there is significant over distension. We should come down on the PIP or the lung will go for a pneumo. Now coming to the pressure volume loop, again other things. Yeah. So here from these loops, we can see which one is the control breath, which one is assisted, which one is a spontaneous. Assisted, there will be initially there will be negative deflection followed by the positive loop. So in the spontaneous one, we can see this entire inspiration is on the negative side. In ventilator breaths, all the entire thing will be on the positive side, because we know the negative, there will be negative intrathoracic pressure when we start our inspiration. This is why it is on the negative side. So from this, we can identify is an assisted breath or a controlled breath or a spontaneous breath. Can you identify what is the graph here? Yeah, here it is actually the figure of fate. This is actually a flow starvation. So the VT is inadequate to meet the patient need. So actually we can see in the upper part of the PV loop, there is a reversal of the inflation and deflation. This is represented as a figure of fate appearance. So what we have to give? We have to give additional flow, we have to give additional volume, we have to prolong the inspiratory time, so that flow starvation will be reduced. So this is how. So there is a flow starvation with a figure of fate appearance. We increase the flow from 6 liters to 8 liters, that flow starvation has disappeared. So this is an adequate inspiratory flow. So from the pressure volume loop also, we can identify this flow delivery is adequate or not. Now coming to another important thing which we can identify from the flow, from the pressure volume loop is airway resistance. So we already discussed that, and from the compliance axis, if you are drawing a line, that is a line from the midpoint of the this inflation limb or the deflation limb to the compliance axis, we can see the resistance. So this is inspiratory resistance, this is expiratory resistance. If you are drawing a line here, we can see that the resistance has been increased. Actually, the curve has bulged like this. Here also we can see that it is increased to this side. So here is more expiratory resistance, this is more inspiratory resistance. So inspiratory resistance may be due to kinged ET or patient biting the tube. So this is how we can identify the airway resistance from a pressure volume loop. So many things we can identify from a pressure volume loop. Actually, it is very helpful. Now coming to air leak, how we can see the air leak in a pressure volume loop. Frequently we are seeing this one. Yeah, we can see that we already told the inspiration started, but expiration is not touching the baseline. This means already the air has leaked out. There is no air to complete this. So already air has been leaked out. So the expiratory portion of loop is not touching the baseline. Now coming to the flow. So many things we have learned from the pressure volume loop. Now we are going to flow volume loop. Actually, flow volume loop is not having much compared to the pressure volume loop. So the most important thing is one is flow scalar, and second one is pressure volume loop. This both will give a lot of information. Now coming to the flow volume loop, what we can learn from flow volume loop. So in the flow volume loop, what here also we can see that the volume is displayed on the x-axis. In the pressure volume loop, pressure was displayed on the x-axis. Here the volume is displayed on the x-axis and flow on the y-axis. Like the pressure volume loop, this also has an inspiratory and expiratory component. Both are in opposite directions. And similarly, this is also not been standardized. In some textbooks, we can say the inspiration will be up. In some textbooks, inspiration will be down. In ventilators also it is like that. And also the clockwise or counterclockwise all depend upon, it is not standardized. So there is no standard convention for any of this. So we have to see how it is represented in our ventilator. Okay, so again, the inspiration, we can see the inspiration here. The inspiration is represented in the upper part and expiration in the down part. So here the inspiration begins the origin of the graph. That is a zero flow state. It increases and reaches the peak inspiratory flow rate. Then it decreases, then flow then decelerates and reaches the zero flow state. And so at this point, we can see the maximum tidal volume attained. So it is crossing the x-axis. So that is the point where it crosses the volume axis, representing the delivered VT. And again, the expiratory flow decreases, which reaches the peak expiratory flow rate. But we can see suddenly it is reducing. It is having a slope more when compared to the inspiratory flow rate because of the elastic forces of the lung, and it reaches the zero flow state. So this is how the flow volume loop, and what and all we can learn from the flow volume loop. These like air leak, air trapping, airway resistance, flow limitation, secretions, all these things can be identified from the flow volume loop also. And this is the shape of flow volume loop in a volume control and a pressure control. So in the volume control, we already told there is a constant flow after reaching the maximum peak inspiratory flow rate. So that is some like square shape. And here we can see reaching the maximum, then decelerating. So a decelerating flow, which we are seeing in a pressure control. So this is flow limitations. So in flow limitation means this graph we can see the expiration is represented in down. This is from Goldsmith, and inspiration is represented in the downward, and it is like a counterclockwise. So here we can see this expiratory flow axis is being limited. So we can say progressive expiratory flow limitation. This is seen in obstructive airway disease mainly. It is known as sky slope loop, mainly seen in BPD. Then here we can see both inspiratory and expiratory flow has been limited. So the common conditions, yeah, it is seen in subglottic stenosis or with a very narrow endotracheal tube. So extrathoracic airway obstruction with both inspiratory and expiratory airflow limitation. Now, how we can identify the inspiratory increased airway resistance from a flow volume loop? Yeah. So we can see actually this expiration, the PEFR, as similar to the flow waveform we already discussed, the PEFR has been reduced and there is a scooping up pattern. So this PEFR reduction itself means that there is some resistance to the airflow, and also the airflow, the flow has also been scooped out. So this is a classical picture of increased airway resistance in a flow volume loop. So this is the how we are seeing in ventilator. So we can see that the peak expiratory flow rate that has been reduced. So after giving salbutamol, after giving the nebulization, we can see that the peak expiratory flow rate has been improved. This is already been seen in the flow scalar also. Now coming to air trapping. Air trapping we can see in the flow waveform also. We can see that we already seen in the the flow waveform. We're coming to the flow volume loop. We can see that this expiration is not touching the baseline. So some gas has been trapped inside the lungs, is not going out. Then next thing is air leak, which we already seen in the volume waveform, in the pressure volume loop also. Now we are going to see in the flow volume loop. So here we can see that it is prematurely terminating. This expiration is terminating before. So this is what is leak. It's not reaching here. Before that itself already been, this amount of air has already been leaked out. So it is prematurely terminating. So this air leak we can see in three things. One is volume waveform, which is shoulder cliff pattern, the PV loop, and the flow volume loop. Now, how to identify the secretions? We can see like many serrations in the expiratory side. This is usual thing we are seeing in our babies. Now, if time, we can go to see some examples. So this is a case scenario. A 6-day-old female newborn at 26 weeks has been relatively stable, receiving assist control with volume targeting. Nurse calls you to the bedside because ventilator is alarming with a high pressure, and the tidal volume is only 2.5 ml per kg. But we have to see that baby was stable. Suddenly this happened with a high pressure alarm, and volume is only 2.5 ml per kg, even with high PAP of 30. We have kept a volume targeting mode, and the previous pressure requirements were only 20-22. Suddenly this happened. So what is your best response? Any answers? So usual case scenario while we are taking our duties. Yeah, sorry. Yeah. Yeah. So yeah. So what is the answer? Here is that we see a low VT in spite of a high tidal volume. So two possibilities are there. One, the lungs suddenly became stiff. But we already told that the baby was stable till then. Suddenly cannot happen. So the thing which more common, more chances a leak. That is, the gas is not reaching the alveoli. Somewhere it is leaking. So next best response is to see the waveform. Both VT and PV and other also we can see to compare the inspiratory and expiratory volumes. That is the best response. So what was the? So we can see the flow volume and the pressure volume loop. You can see here in the flow volume, we can see that this expiratory expiration has been prematurely terminated. Here it has been terminated, it's showing a significant leak. Here also we can see that it is not actually this expiratory limb of the PV loop. It is not touching the baseline. This is actually ventilator drawing this line. So it is like this from here to here. So both of these are showing air leak. So also in the volume waveform also we can see the air leak. We can see that this expiratory limb of the volume is not touching the baseline, the shoulder cliff. You can see that cliff pattern. So that is the answer. So can anyone tell what is this? Okay, we can see Nare turbulence, Madhuri. This is actually secretions. So what is this? This is a flow waveform. You can see the here already the flow has reached to stereo state, but still the inspiratory time is, since the inspiratory time has been set to a certain value, inspiration is continuing. So this is excessive TI and we changed into the flow cycling, then it has become better. Okay. So what is happening here? Yeah, very good. That is actually air trapping. We can see that this expiratory flow is not touching the baseline. Before that, another breath started. So we actually reduce the E time. So we are giving enough E time so that lungs can empty. So in the next graph, we can see that this is touching the baseline. Okay. So what is this? We can see in the expiratory limb some problem. This is inspiration, this is expiration. Some expiratory airflow limitation. Initially, it was expiration was okay. At the end of the expiration, some issues are there. You have done a scopy. It was a tracheomalacia. So thank you. So any questions?
Hello. So thank you, Dr. Jean, for the wonderful presentation. It was indeed a treat, visual and auditory treat to all of us. And in fact, I also learned a lot of new things about the pulmonary graphics. And in fact, I don't have anything more to add to the presentation, which was really wonderful. And if there are any questions from the audience, please put it in the chat box. There is one question from Is there anything to in pulmonary graphics to indicate selective right lung intubation? Is there anything, Jean, you would like to take that question? Is there anything in pulmonary graphics to indicate selective right lung intubation? Hello?
Ventilation alone, I don't know, sir. Actually, we are seeing
So,
together, no.
yeah, probably, the flow, everything is directed towards one lung. So, if it is a volume targeted ventilation, tidal volume will not be achieved, and the pressure reached also would be high. So, probably in a volume targeted ventilation, you can identify based on these two alarms, I think. In a pressure targeted ventilation, I'm not sure whether you can, you will not be able to achieve the tidal volume you would want to achieve, but there will not be any particular alarm or waveform changes which you can probably identify. That is my guess, but I don't know whether anything particularly this has been discussed anywhere in any textbook. Okay, then if there are no more questions, we will close the discussion. Thank you again for the wonderful presentation.
Thank you, sir. Thank you, everyone.